let's get started here on this next chapter, chapter 18. You see that we got a few different functional groups that were thrown together in this chapter. Ethers, epoxides, thiols, and sulfides. Okay, and truthfully, these are all grouped together because they are kind of boring functional groups. These are some of the least reactive functional groups. The big exception on this list here are the epoxides. Epoxides are incredibly reactive. Let's take a look at an example of each of these here. Okay, so an ether is when you have an oxygen that's sandwiched between two carbon groups here, two alkyl groups. So for example, if I have an oxygen, and this is kind of the most common ether in the world. Sometimes it's even just called ether instead of by its real name here, but if you have two ethyl groups coming off of that oxygen. Very, very common solvent in organic chemistry. And we'll talk about nomenclature of ethers here in a second. Okay. An epoxide is actually a type of ether, but it's a very, very specific type of ether where you have this oxygen in this three-membered ring. All right, so it's a cyclic ether. Okay, and it's always got to be three-membered ring to be an epoxide. There could be even more carbons. This is the smallest possible epoxide. Okay, but it's got to have that three-membered ring in there, and that's why they're so reactive, because three-membered rings, if you remember, aren't very happy. There's a lot of angle strain going on in this ring. Okay, a thiol is analogous to an alcohol, but using a sulfur instead. So a thiol has an RSH group. Okay, remember, sulfur lives right under oxygen on our periodic table, so it's got the same bonding pattern. Sulfur likes to have two bonds and two lone pairs. All right, and then a sulfide is sort of analogous to an ether, but using a sulfur. So RSR. We have the sulfur in the middle. All right, so these are our four functional groups for this particular chapter here. All right, and since we got a few different functional groups in the mix here, this is a good time to sort of take a step back and revisit a topic that we spent some time talking about the first semester, and that is boiling points. All right, so let's just take two compounds here. We're going to look at propane, okay, and then a compound that's very similar in terms of its size, but I'm going to replace that one of those carbons with an OH, so ethanol here. All right, and looking at these two structures, we should be able to tell which one has the higher boiling point. Okay, so first of all, what do we think? Propane or ethanol? Which one has a higher boiling point? Ethanol. And why? What are we looking for when we're looking and comparing boiling points here? What is it about ethanol that makes it a higher boiling point? Absolutely, right? So this boiling point, right? Let's just remember in our head here, if we have this compound, okay, that's in the liquid phase here. All right, that means that all of those molecules are sitting there close together with one another, interacting very strongly with one another. If we then boil this substance right here, What are we doing? We're breaking those intermolecular interactions between those neighboring molecules. Right? So this boiling point we really use as a stand-in, as a measure of how strongly neighboring molecules are interacting with one another. Right? So when we say boiling, really what we're doing is breaking intermolecular interactions. Right? So absolutely, ethanol has a boiling point around 78 degrees Celsius. That number isn't really important. We're just going to use these values to compare. All right? Compared to propane, which has a boiling point of negative 45 degrees Celsius. Okay, so first of all, what does that mean? Let's look at these numbers real quick. Ethanol, I think we all know, is a liquid at room temperature. But what about propane? What would propane be at room temperature? A gas, right? Because its boiling point is really, really low. So at room temperature, it's already in the gas phase. Okay? And yes, that's because ethanol here has these hydrogen bonding interactions because of that OH group. And propane doesn't. It has only what are called dispersion forces, which are the weakest of all of the intermolecular interactions. Okay, so now let's think about our new functional groups here. Now what about an ether? What if I shuffle around this ethanol here and just put that oxygen in the very middle of the compound? Okay, what do we think? Will it have a higher or a lower boiling point than this 78 degrees here? Should be lower, because now I don't have any hydrogen bonding interactions. Remember, in order to hydrogen bond, you have to have an OH or an NH bond. You can also have an FH bond, but that's talking about one very specific molecule, hydrofluoric acid, HF. Okay, so I don't have one of those OH bonds in here. And so indeed, this molecule is also considered to be a nonpolar molecule. It only has these dispersion forces available to it. But what we're going to see is because of the lone pairs on this oxygen, it's a little better at dispersion interactions than just a normal old alkane, but still has a very low boiling point. So this still has a low boiling point of negative 25 degrees Celsius. If we want to look at another one of our new functional groups up here, thiol. So now I'm going to replace, instead of ethanol, we're going to look at an SH bond here. Okay. Can this molecule hydrogen bond? It's got that SH there, right? But remember, in order to be hydrogen bonding, you have to be one of these three specific bonds here. Okay? Okay, hydrogen bonding is just a type of dipole-dipole interaction, but it kind of gets its own name because if you're one of these three bonds here, you form really, really, really strong dipole-dipole interactions. If it's not on that list, OH, NH, or FH, this would just dipole-dipole interact. So it's still considered to be polar. All right. These aren't as strong of interactions as you would get if you had these hydrogen bonding, but they're still stronger than just dispersion forces. This molecule right here has a boiling point around 35 degrees Celsius. Okay, so you can see still quite a bit higher than are ether, but not quite as high as an alcohol. All right, and then lastly, just on the other extreme end here, if we took a carboxylic acid that was around the same size of all these other molecules here, this molecule right here is capable of the strongest types of interactions here. Not only can it hydrogen bond with that hydroxyl group, it's also got that polar carbonyl group in there that can dipole-dipole interact. All right, and so these carboxylic acids have the highest boiling point out of all of our compounds. This one's about 100 degrees Celsius. All right, and so again, just to compare our ether and our alcohol here, you see we have a huge difference in these two boiling points. These have the same molecular formula. These are constitutional isomers of one another. But when I move that oxygen to the middle of my molecule, it can no longer do those really strong hydrogen bonding interactions, and it's only got those non-polar dispersion forces, making it have a much lower boiling point. Okay. Cool. We're going to sort of focus a lot today on ethers. These are not terribly reactive functional groups. There are a few reactions of ethers we're going to learn. But first things first, we're going to do our ether nomenclature. Okay? And ethers, as far as functional groups go, we have our normal IUPAC nomenclature that we have to know, but ethers in particular are more often referred to as their nicknames, what we call common names. And that's where we're going to start. So your common names, remember your ethers, you always have alkyl groups on either side of your oxygens. Okay, so step one is you're going to name each alkyl group. So what do I mean by that? I mean I'm going to look on one side, the left-hand side of this oxygen. There are 2 carbons here. Right? That's what we would call an ethyl group. We jump to the other side. There's 1 carbon. That's what we would call a methyl group. All right, and then all we're going to do is we're going to put these together in alphabetical order, followed by the word ether. All right, so put in alpha order. Followed by ether. All right, and because these are common names, we're going to see something we very rarely see in our nomenclature schemes here, and that is spaces in our name. So this molecule right here would be ethyl space methyl space ether. All right, so let's just do a few examples here. Again, this one with 2 ethyl groups is going to be the most common one. This is sometimes even referred to as just ether. Okay, but strictly speaking, that's not enough information here. So again, I'm going to look on both sides. This is an ethyl group. On the other side is also an ethyl group. So since we got 2 of the same thing, what are we going to put in front of that name? Di. So this would be diethyl ether. All right, so one more you guys are going to do on your own. Excuse me, thank you. Thank you. All right, so this one, we have 1, 2, 3, 4 carbons on this side, so this is a butyl. Hop to the other side, we have 1, 2, 3 carbons, so this would be a propyl group. We're going to put them in alphabetical order: butyl, propyl, ether. Okay? So these are our common names for ethers here. Again, very commonly referred to by their common names, as opposed to some of the other functional groups where really they're just strictly referred to by their IUPAC names. The only limitation here is this is really only going to work out for pretty simple ethers here. Right? As soon as you start adding branch points in there and that sort of thing, it completely throws off this whole scheme. So this is something we need to be able to do for these simple straight chain alkyl groups on our ethers, is be able to come up with the common name of that molecule. Okay. The one that we're going to do that's going to apply to everything is going to be our IUPAC nomenclature. Well, go back. All right. So in addition for common names for ethers, we're also going to learn the IUPAC nomenclature. Okay? And before we get started, the important thing to remember about ether nomenclature is that that ether group is considered to be a substituent, not a functional group that has priority. So ether groups are substituents. We treat them like alkyl groups are like our halogens, right? So our alkyl groups, the ethyls, the methyls of the world, or the halogens, the fluoros, the chloros, the things that come out front of our name, right? That means that there's no priority associated with this ether functional group here. So let's just do our example that we started out with before. All right, so we're going to go step by step. Step 1 is to find the parent chain. All right, and so for this, how do we find a parent chain with that oxygen in the middle? We're going to look on either side of our oxygen and figure out what the longest continuous set of carbons is, right? So whichever chunk is the bigger chunk in your ether, that's considered to be the parent chain. All right, so for ethers, we're going to look at the alkyl group on either side of the oxygen. The longest continuous carbons is the parent. All right, so I'm going to look at this side over here. and compare it to this side over here. Which one's my parent chain, on the left or the right? The left. All right, so this 1, 2 carbons is my parent chain here. I kind of did. I'm gonna switch this up. We're gonna add 1 additional carbon on here, and I'll show you why here in a second. Okay, so this is actually going to be 3 carbons on this left-hand side here. Okay, so then step 2, we got to find and name our substituents. The other side, the side that's not my parent chain here, this whole thing is then going to be considered a substituent in my molecule. So that ether oxygen plus the smaller alkyl group that's my ether substituent. Okay, so then how do we name these ether substituents here? Okay, so it's going to be the number of carbons, just like we always use, that's prefix for. So this 1 carbon over here would use which prefix? Meth. So it's actually just going to be the prefix by itself, right? The meth. And then you're going to add on to the end oxy. So this substituent right here would be a methoxy group. Okay, so then step 4 here, we're going to number our parent chain. We're not going to prioritize that ether group because it's not a functional group, it's a substituent. Nonetheless, we still want the lowest possible numbers to appear in our name. So in this case, this methoxy group is on carbon 1. All right, and then we're going to assemble the name, putting everything in alphabetical order. And I guess under number parent chain, let's just make sure to state explicitly here that ethers do not have priority. Like a methyl group or a fluoro group, you don't prioritize that particular substituent. You just make sure that your name has the lowest possible number. Okay, so then putting it all together, this would be 1 methoxy propane. We have that methoxy group on carbon 1, and we didn't do anything to the back end of this parent chain, right? The parent chain is still propane. Right, all of that information of that ether functional group is a substituent that goes out front of the name. All right, so let's practice a few of these here. Let's go back, and we did the common name for this one before. Now let's do its IUPAC name. so I'm going to look at this molecule here. I got to first figure out which chunk is my parent chain. The one on the left or the one on the right, all right? And the larger fragment would be considered the parent chain. So that'd be these 1, 2, 3, 4 carbons here. So then this ether group here, this whole thing is considered to be my substituent. I got these 3 carbons, so this would be a propoxy group. Okay, if I'm going to number my parent chain, I'm going to start counting from over here so that that ether substituent is on the lowest possible number. So this would be 1 propoxy butane. Okay, so now I'm going to look at my next one here. And let's see, we're going to compare this group on this side to this group on this side. Which one's going to be my parent chain, red or blue? The red. The longer set of continuous carbons here, these 1, 2, 3, 4, 5, 6 carbons. This is my parent chain. So we got 2 substituents here. We have a fluoro group. And now we have a 2-carbon ether group here. So what would we call this 2-carbon ether group? An ethoxy. Okay, we got to number our parent chain. 1, 2, 3, 4, 5, 6. Or we can go the other way. 1, 2, 3, 4, 5, 6. And remember, there is nothing special about this ethoxy group. It does not have any sort of priority, so we're looking to just have the lowest possible numbers in our name. In the red numbering scheme, it's a 2 and a 4. In my blue numbering scheme, it's a 3 and a 5. So then which one am I going to pick? The red one, right? Again, I'm not paying attention to just the ethoxy. There's no priority business to think about here. So it's just whatever gives me the lowest number in my name. All right, so then putting this all together in alphabetical order here, this would be 4-ethoxy, 2-fluorohexane. Okay, and so here we had this extra substituent, this fluoro group in my parent chain. If we look at this one though, we have a little bit of a unique situation. So first of all, what's going to be my parent chain, the blue or the red? The red, the longer continuous set of carbons. So then how do I deal with this branch point here in my ether substituent? Okay, so let's remember we sort of first encountered these talking about alkane nomenclature. So let's just take a big alkane. Was that 2, 4, 6, 8? Sure, cool. And then if we had this branched alkyl group coming off of it, okay, there was this common name for this group here. There are 3 carbons, so we could have called this 1, 2, 3, 4. So 4 isopropyl octane. Okay, but we also had ways of more systematically naming these groups right here, these branched alkyl groups. So this isopropyl group here, we could also call, in parentheses, 1-methyl ethyl. All right, so we could have also said that this is 4-1-methyl ethyl octane. All right, because if we look at our branch substituent here, we're going to sort of play that same game where we then go, okay, say within this substituent, this is the longest continuous set of carbons. So there's this methyl group coming off of that first carbon. So this would also be called a methyl ethyl group, 1-methyl ethyl. All right, we're going to play a very similar game here. We're going to say, all right, these 1, 2, 1, 2, 3, 4, 5 carbons here are my parent chain, and my substituent is coming off of carbon 1 here. But now this whole thing is my substituent. Without this extra methyl group on there, this would be an ethoxy group, right? Now that I have that extra methyl group on there, I'm going to then number this substituent here. You're always going to start with carbon 1 being bound to that oxygen. So this group right here would be a 1-methyl ethoxy in parentheses group. So putting it all together, this would be 1. That's indicating where it is on my parent chain. Then I got to name the substituent, the 1-methyl ethoxy group. Close the parentheses, pentane. Okay, or we could refer to this using those common names here. We do have a common name for this branched group. So this would be isopropyl pentyl ether. Right, the top one is what we call the IUPAC name. As a reminder, the IUPAC, that's the international organization that hammered out all these rules. Groups of scientists got together and were like, look, we can't keep calling everything different things. We call it one thing over here in America, you call it one thing over there in France. Let's just set some ground rules here. Or the common name. Cool. All right, so this is going to be a good time to bring back these branched alkyl groups and remind ourselves of how we went about naming those. That was one of the first things we covered when we covered alkanes. Okay, so reactions of ethers. All right, so the first, we're going to have, there's really not very many reactions of ethers. Really just how they fall apart and how we put them together is kind of the basics of it here. So we have acid catalyzed decomposition of ethers. Okay, so if we have an ether, we'll take diethyl ether. And we have one of our hydrohalogen acids here. Let's do HBr. Actually, I'm going to do a mechanism here, so I'm going to draw out bonds. All right, we will see this ether decompose. It kind of splits it apart at that oxygen. So we would get an alcohol and an alkyl halide. Okay, and the first step here is going to be similar to what we saw in some of our alcohol reaction mechanisms here. One of the things that's going to help us break this molecule apart is we're going to protonate that oxygen. that converts our ethoxy group from being a terrible leaving group to now being a good leaving group. Okay, so then the last step here is then going to be this SN2 substitution mechanism. Our nucleophile, the bromide ion, is going to attack the carbon from one side, kicking off that leaving group. Okay, and we're just going to note that this step here, after this protonation, this is an SN2 mechanism. We talked about those last week, right? Really, they were a review from the first semester. Okay, we have an SN2 mechanism here. So importantly, what that also implies is that whichever one of these carbons is more easily accessible, that's going to be the one that gets attacked, right? A big limitation to these SN2 mechanisms are if your nucleophile can actually get to the carbon here. In this case, our ether was symmetric, so it didn't matter, but that may not be the case. So let's just say the more accessible carbon gets attacked. All right, so why is that relevant? Let's do another example here, but instead now I'm going to take an asymmetric ether. I'm going to treat it with HBr. All right, and I want you all to take a second and tell me what the products of this reaction would be. All right, we're going to get an alcohol and an alkyl halide just like we got before, but the question is which half is which, right? So let's look at the mechanism again, see if we can't help that, have that help us figure it out. Again, step one, let's protonate that oxygen. All right, so now I have this good leaving group here, because it'll leave as an alcohol as opposed to an alkoxide ion. Okay, so that's step one. But now step two, we have our bromide. And we need to do this SN2 mechanism. So it's either going to attack this carbon over here, breaking this bond, or it could attack this carbon over here, breaking the bond on this side. Which one of these two steps is going to be more likely here, the red or the blue? We said this is SN2. It's the more accessible carbon that gets attacked here. Which one of these carbons is more accessible? This blue one over here or this red one over here? The blue one, right? The red one is super duper crowded. There's no way for that bromide ion to actually get in there. So our actual mechanism here will be breaking this bond. So we can see that we will get a methyl alkyl halide, bromomethane, and the alcohol fragment will have that more crowded carbon on there, T-butanol. All right, so again, SN2 mechanism, the more accessible carbon gets attacked. All right, now, one of the thing about this mechanism here is it's pretty, about this reaction here, is it's pretty balanced at equilibrium. So we can really throw this into, rather drive this reaction in one direction or the other, depending on what we have an excess of. So our next reaction here is going to be essentially the exact opposite of the reaction that we just saw. Okay, again, acid catalyzed. And now we're going to synthesize this ether. Okay, and we just want to make a note here that this is a great way of creating symmetric ethers. So for example, if we take some propanol and we have some acid catalyst here, so I'm going to use hydronium. All right, what we're going to find is we get this symmetric ether. All right, so first of all, if we're looking carefully here on both sides, I went from having this 3-carbon alcohol to now having a 6-carbon ether. So how did that happen? If I'm being good with my balancing here, how many alcohol molecules are reacting with one another? 2. So let's just put them side by side because we're going to need to play the spot the difference game here. Let's look carefully and try to figure out what new bonds are being formed in this reaction. All right, and what bonds are being broken. Okay, so you're going to go in and you're going to highlight any new bonds that are formed and any bonds that are broken. All right, so what new bond gets formed in this reaction? Yeah, I got this new carbon-oxygen bond that's formed over here, okay? I have one of those carbon-oxygen bonds on my reactant side, but I gotta form this new one as well. So then what's gonna need to get broken over here on my reactant side? So one of these alcohols is gonna have to lose its oxygen. All right, there's not two oxygens in my product, so one of them is going to have to go. The other alcohol can keep its oxygen, but it is going to have to lose that hydrogen. All right, so when we're working through these mechanisms, step one is spot the difference game. What is being broken in this reaction and what new bonds are being formed in this reaction. And we can see that if we're looking and we're making our balanced chemical equation, which we rarely do in chemistry or organic chemistry, but we would also have water as one of our products, right? We're losing an OH from one and a hydrogen from another. All right, so now that we've established what bonds are being broken and what new bonds are being formed, let's look at the mechanism here. Let's see if we can't figure this out here. What do we think the first step is going to be when we have this alcohol under acidic conditions? All right, I'll give you a hint. This is going to act as an acid because it's an acid, right? That's my proton donor. So what's going to be accepting the proton in this reaction? The oxygen, absolutely, right? So step one is we're going to protonate that alcohol group. And similar to what we saw before, this will turn it into a good leaving group. All right, so we have one of our alcohol groups is protonated. Okay, so H2, take off a lone pair, put a plus sign. All right, and just like we saw in our previous chapter here, that converted this alcohol group into this good leaving group. All right, and so that's what's going to happen, is it's going to get kicked off. All right, so this carbon right here, it's going to play the role of the electrophile. Right, when that gets attacked, that leaving group will be kicked off. What is it that's playing the role of the nucleophile? Exactly, the oxygen on my other alcohol. Right? And that's my new bond that will be formed, my new oxygen-carbon bond that will be formed. One of those oxygens will attack that carbon, kicking off that good leaving group. All right, there's just one more step to go here. My ether still has that extra hydrogen on there, so we need to remove that hydrogen. What is it that plays the role of a proton acceptor under acidic conditions? Water, right? You can't have hydroxide, that's too strong of a base for acidic conditions. So for this, we will just use water. And that will reform our acid catalyst. Okay, so the first step here is a step that we saw a lot in our reactions of alcohols where we protonate that OH group, which turns it into a good leaving group. So now that's our electrophile. The second molecule of alcohol plays the role of the nucleophile, and that's how I get my new carbon-oxygen bond. We're under acidic conditions here, so in order to remove that last hydrogen, we need a proton acceptor, and under acidic conditions, that would be water. Cool. All right, so this is a great way of creating symmetric ethers here. Just add, you have a bunch of alcohol with some acid catalyst in there, and you will create your symmetric ether. Okay? But what about an asymmetric ether? How do we go about making those? This is using what's called a Williamson ether synthesis. Okay, and this will be our method of creating asymmetric ethers. All right, so what we can do so step one is we're going to take an alcohol here and we're going to treat it with sodium hydride. All right. This sodium hydride here, this is a very strong base. Right, now we're talking about something that's much stronger than, say, a hydroxide ion. We're now in that next sphere of really good bases. And what happens when we put an alcohol with a really, really good base? It's going to lose that hydrogen, right? Become what we call an alkoxide ion. So first of all, do y'all remember what I told you to do every time you see sodium in a compound? Erase it and replace it with a negative charge. That metal ion is never doing anything for you. So this thing right here, this hydride is our base. Okay, and absolutely it's going to deprotonate this alcohol. So that negative charge is going to grab that hydrogen and break that bond. Okay, so this creates what's called an alkoxide ion, which we know to be a good base, but also a good nucleophile. So in step two, after we've treated it with that sodium hydride, now we're just going to add in a good electrophile here, an alkyl halide. So in this case, we'll just do a methyl halide here. Okay, so my reaction here, that nucleophile is going to attack that electrophilic carbon and kick off that leaving group. Okay, and in this way I will have combined that alcohol group with that alkyl halide to create this asymmetric ether. right? What can we say about this mechanism right here? What do we call these? These concurrent nucleophile attacks and leaving group leaves all at the same time substitution reactions. This one's a SN2. So we have a similar consideration to what we were talking about before. Right? The accessibility of that carbon is going to tell us how successful this reaction is going to be. Okay? So we have a similar consideration to what we were looking at before. Okay, I'm going to tell you that we're going to do a Williamson ether synthesis here to create this ether. Right? I want to make this asymmetric ether here. So I want to know what alcohol and what alkyl halide I should be using. All right, everybody take a second and see if you can't draw the alcohol and the alkyl halide that we would use to create this particular compound. All right, so there's two possibilities here, right? I can either say, all right, I'm going to break this right here. That means that my alcohol would be that bigger fragment, the tert-butanol. And my alkyl halide would be this methyl halogen here. Or I could say that my new bond was on the other side here. So this would mean that my alcohol was that methanol. Okay, and my alkyl halide would be the bigger chunk. Right? In theory, both of these would produce that same product. Okay? But one of these methods is way more preferable than the other one. Okay, and so let's look at that second step in our mechanism where I have my deprotonated alcohol. And it's going to attack that carbon at the base of my halogen. All right, so let's just which one of these two is going to be more efficient here? The top one where my alkoxide ion is attacking that methyl carbon, or the bottom one where my alkoxide ion is attacking this tertiary carbon here? Right? The more accessible carbon is much easier to gain access to, right? So this top combination here, where the big group is the alcohol fragment, and the smaller group is your alkyl chloride, or alkyl bromide, whatever it is, right? So the more accessible fragment should be the alkyl halide. because it's the electrophile in that SN2 step. All right, the more accessible that carbon is, the better it is at being an electrophile. So when we're doing our Williamson ether synthesis, we want to make sure that the fragment that is the chloride fragment or the bromide, the alkyl halide fragment, is the more accessible carbon of the two. All right, we're going to leave it there. That covers our reactions of ethers. Again, they're not all that crazy reactive of a functional group. We're going to end things a little early because I'm going to let you guys view your exams. Okay, so to be clear, in my course, the exams are mine. They're kept confidential, so I'm going to pass them back. You guys can ask any questions that you want, but no notes or no pictures, and they don't leave this room. Right? I'm going to collect everything back at the end here. So everybody take a second to pack up your stuff, and then I'll pass back your exams to view.